Welcome to this problem walkthrough. Today, we'll explore problem number 19, remove nth node from end of list. This is a classic linked list problem that challenges us to remove a specific node from the end of a singly linked list in an efficient manner. We'll break down the problem, explore the intuition behind it, and walk through different approaches. Let's dive in. In this problem, we are working with a singly linked list and an integer n. The task is to remove the nth node from the end of the list and then return the updated head of the list. The input consists of two components: first, the head of the linked list, which represents the starting point of the list, and second, the integer n, which specifies the position of the node to be removed when counting from the end of the list. The constraints ensure that n is always within the valid range, from 1 to the length of the list. The output is straightforward. After removing the specified node, we return the modified linked list's head. Let's look at an example to clarify this further. Consider a linked list with elements 1, 2, 3, 4, and 5, and n equals 2. Here, the second node from the end is the node containing the value 4. When we remove this node, the linked list becomes 1-2-3-5, as the connection between 3 and 4 is broken, and 3 now directly points to 5. This modified list is returned as the output. In a different example, if the linked list has only one node, 1, and n equals 1, the task is to remove this single node. The result, in this case, is an empty list, represented as. Now, consider another case where the linked list has two nodes, 1 and 2, and n equals 1. The first node from the end is the node containing the value 2. Removing this node leaves us with just the first node, 1, resulting in the list 1. Along with these examples, we have some constraints to keep in mind. The number of nodes in the linked list will always be between 1 and 30, and each node's value will be between 0 and 100. Importantly, n is guaranteed to be a valid position within the length of the list, so we don't need to handle cases where n is out of range. There are also a few edge cases to consider. If the list contains only one node and n equals 1, removing this single node will result in an empty list. Similarly, if n equals the length of the list, the first node will be removed, effectively shifting the head of the list to the second node. Additionally, valid inputs ensure that we don't encounter invalid n values, but our solution should be robust enough to handle small lists, such as those with just one or two nodes, as well as cases where n points to the first or last node in the list. Handling these scenarios correctly will ensure our solution is complete and reliable. When approaching this problem, we first consider the brute force method, which involves two passes through the linked list. The intuition here is simple: the nth node from the end corresponds to the length n plus 1 th node from the start. To achieve this, we start by traversing the list to calculate its total length, denoted as L. Once we have the length, we can determine the position of the target node by using the formula L n plus 1. With this position in hand, we traverse the list a second time to locate the node and adjust the pointers to skip over it, effectively removing it from the list. Although this approach is straightforward and easy to implement, it requires two full passes over the list, making it less efficient for long lists. The time complexity is O(n), due to the two traversals, and the space complexity is O(1), since no additional data structures are used. Now, to optimize the process, we can use the two-pointer technique, which allows us to locate the target node in a single traversal. The key insight here is to maintain a gap of n nodes between two pointers, commonly called the fast and slow pointers. Both pointers start at the head of the list, and the fast pointer is moved n steps ahead first. After this, both pointers move forward together, one step at a time, until the fast pointer reaches the end of the list. At this point, the slow pointer will be positioned just before the nth node from the end. By adjusting the slow pointer's next reference, we can skip over and remove the target node. This method is highly efficient, as it only requires one traversal of the list, resulting in a time complexity of O(n). Additionally, it uses constant space, making it an excellent choice in terms of efficiency. However, every approach comes with trade-offs. While the two-pointer technique is efficient, it does involve slightly more complex pointer manipulation compared to the brute force method. Additionally, there's the recursive approach, which offers an elegant and concise solution. In this method, we use recursion to traverse the list to the end and then backtrack while keeping track of the node's position from the end. During backtracking, we identify the nth node and adjust pointers to remove it. While this method achieves an O(n) time complexity since it traverses the list only once, it requires O(n) space due to the recursive call stack. This can lead to stack overflow for very long lists, making it less reliable in scenarios where input size is large. Thus, while elegant, the recursive approach is less practical for general use. Given the trade-offs of the different approaches, the two-pointer technique emerges as the most balanced strategy for this problem. It combines efficiency with simplicity, avoiding the overhead of recursion and reducing the number of passes needed compared to the brute force method. The crux of this method lies in the observation that maintaining an n-step gap between two pointers allows us to directly identify the target node in a single traversal. This insight eliminates the need to calculate the list's length or to backtrack. While managing two pointers adds minor implementation complexity, the performance benefits far outweigh this trade-off. With an O(n) time complexity and O(1) space usage, the two-pointer approach is both robust and scalable, making it the ideal choice for solving this problem efficiently. This problem challenges us to remove the nth node from the end of a singly linked list in just one traversal. To achieve this efficiently, we use the two-pointer technique. The intuition behind this approach is quite elegant. By creating a gap of n nodes between two pointers, a fast pointer and a slow pointer, we can ensure that when the fast pointer reaches the end of the list, the slow pointer will be perfectly positioned just before the node we need to remove. The process begins by initializing both pointers at a dummy node, which is a helpful construct that simplifies edge cases, such as when the head node itself needs to be removed. This dummy node is linked to the head of the list, and both the fast and slow pointers start from this position, ready to traverse the list strategically. The first step in this approach is to advance the fast pointer by n+1 steps. This additional step ensures the gap between the fast and slow pointers is exactly n nodes. If, for some reason, the list is shorter than n nodes, we handle this scenario gracefully by returning the list as is since no valid node exists to remove. Once the fast pointer is positioned, we begin traversing the list with both pointers. Both the fast and slow pointers move one step at a time until the fast pointer reaches the end of the list. At that moment, the slow pointer will be positioned just before the node that needs to be removed. This setup allows us to remove the target node efficiently by simply adjusting the next pointer of the slow node to skip over the node we want to delete. Finally, we return dummy.next, which points to the new head of the modified list, ensuring the algorithm works even when the head node is removed. There are several key insights that make this algorithm both efficient and robust. First, the use of a dummy node simplifies handling edge cases, such as when the head node needs to be removed. By positioning the dummy node before the head, we eliminate the need for special conditions to manage the start of the list. Next, the two-pointer technique ensures that the slow pointer always lands in the correct position relative to the fast pointer, thanks to the fixed gap of n nodes. This eliminates the need for multiple passes over the list to calculate its length. Additionally, the algorithm gracefully handles edge cases, such as when n equals the length of the list, which results in the head node being removed, or when n exceeds the list's length, where no changes are made. The singly linked list is the core data structure used, with each node containing a value and a next pointer. The dummy node is an auxiliary structure that simplifies edge case handling and ensures the algorithm is clean and efficient. The efficiency of this algorithm can be understood through its complexity analysis. It achieves a time complexity of O(n), where n is the number of nodes in the list, as both pointers traverse the list in a single pass. The space complexity is O(1), because the algorithm operates in place, using only two pointers without any additional data structures. To illustrate the process, consider an example where the input list is 1-2-3-4-5, and n is 2. In the initial setup, we create a dummy node and link it to the head of the list. Both the fast and slow pointers start at the dummy node, which simplifies edge case handling and ensures the algorithm remains robust. Next, we advance the fast pointer 3 steps ahead, which is n+1, positioning it at the node with value 3. This establishes a gap of 2 nodes between the fast and slow pointers. From here, both pointers move one step at a time through the list. When the fast pointer reaches the end of the list, pointing to null, the slow pointer will be positioned just before the node to remove, which in this case is the node with value 4. To remove this node, we adjust the next pointer of the slow node to skip over the target node, effectively linking it to the node with value 5. The modified list is now 1-2-3-5. Finally, returning dummy.next gives us the new head of the list, which excludes the removed node. This example demonstrates the elegance and efficiency of the algorithm in handling the task with minimal traversal and no additional space. To solve the problem of removing the nth node from the end of a linked list, we start by defining a simple list node class that represents each node in the list. It has two attributes, val to store the node's value and next to point to the next node. Then, in the solution class, we define the remove nth from end function. The first step is to create a dummy node with a value of 0. This dummy node points to the head of the original list and helps handle edge cases where the node to be removed is the head itself. We then initialize two pointers, fast and slow, both starting at the dummy node. The next step is to move the fast pointer ahead by n+1 steps. This ensures there is a gap of n nodes between the fast pointer and the slow pointer. Once the fast pointer has been advanced, we move both the fast and slow pointers one step at a time until the fast pointer reaches the end of the list. At this point, the slow pointer will be positioned just before the node that needs to be removed. To remove the target node, we adjust the next pointer of the slow node to skip over the node to be deleted. Finally, we return dummy.next, which points to the head of the modified list. This approach ensures that the linked list is updated correctly, even in edge cases, and the solution runs efficiently with O(n) time complexity. Here, we start by defining our list node class, which represents a node in a singly linked list. Each node contains an integer value, val, and a reference to the next node, next. The constructor initializes the node's value and sets the next pointer to null. Now, in the remove nth from end method, the goal is to remove the nth node from the end of a given linked list. To make the implementation straightforward, we create a dummy node with a value of 0 that points to the head of the list. This dummy node simplifies edge cases, such as when the head itself needs to be removed. We then initialize two pointers, fast and slow, both starting at the dummy node. The fast pointer is moved n+1 steps ahead of the slow pointer using a loop. This creates a gap of n nodes between the two pointers, which is crucial for identifying the correct node to remove. Once the fast pointer is n+1 steps ahead, both pointers are moved forward one step at a time until the fast pointer reaches the end of the list. This ensures that the slow pointer is positioned just before the node that needs to be removed. To remove the nth node from the end, we simply update the next reference of the slow pointer to skip over the target node, effectively removing it from the list. Finally, we return dummy.next, which points to the head of the modified list. Using a dummy node ensures that edge cases, such as removing the head node, are handled seamlessly. This approach is efficient, with a time complexity of O(L), where L is the length of the list, as we only traverse the list once. In this example, we want to remove the second node from the end of the list in the given linked list 1-2-3-4-5. To start, we initialize a dummy node with the value 0 and point it to the head of the input list. This dummy node acts as a placeholder, making edge cases like removing the head easier to handle. Both fast and slow pointers are initialized to point to this dummy node. Next, we move the fast pointer n+1 steps forward to create a gap of n nodes between the fast and slow pointers. After the first step, fast points to the first node with value 1. After the second step, it points to the node with value 2, and after the third step, it points to the node with value 3. At this point, the gap between fast and slow pointers is exactly 2 nodes, as required. Now we simultaneously move both the fast and slow pointers one step at a time until the fast pointer reaches the end of the list. In the first step, fast moves to the node with value 4, while slow moves to the node with value 1. In the second step, fast moves to the node with value 5, and slow advances to the node with value 2. In the third step, the fast pointer reaches none, indicating the end of the list, and the slow pointer is now at the node with value 3. At this point, the node immediately following slow is the one to be removed. To remove this node, we update slow.next to skip over the target node. Before the removal, slow.next points to the node with value 4. After the update, slow.next points to the node with value 5. This effectively removes the second node from the end of the list. Finally, we return dummy.next, which points to the modified list, 1-2-3-5. In this second example, the input linked list is 1-2-3, and we need to remove the last node, which corresponds to n equals 1. As before, we start by creating a dummy node with value 0 and pointing it to the head of the list. Both fast and slow pointers are initialized to this dummy node. Next, we move the fast pointer n+1 steps forward to establish the required gap. After the first step, fast points to the node with value 1. After the second step, it points to the node with value 2. With the gap established, we now move both pointers together until the fast pointer reaches the end of the list. On the first traversal step, fast moves to the node with value 3, while slow moves to the node with value 1. On the next step, fast reaches none, and slow is now at the node with value 2. At this point, the slow pointer is positioned just before the node we want to remove, which is the last node in the list with value 3. To remove this node, we update slow.next to skip over the target node. Before the update, slow.next points to the node with value 3. After the update, slow.next points to none, effectively removing the last node from the list. Finally, we return dummy.next, which points to the modified list, 1-2. Moving on to the third example, we have a linked list with only one node, 1, and we need to remove it. Here, n equals 1, indicating that the node to be removed is also the only node in the list. As usual, we start by creating a dummy node and initializing both fast and slow pointers to it. To begin, we move the fast pointer n+1 steps forward. After the first step, fast points to the node with value 1. After the second step, fast reaches none, indicating the end of the list. Since the fast pointer is now at the end, no further traversal is needed. The slow pointer remains at the dummy node, and the node to be removed is directly after it. To remove the node, we update slow.next to skip over the target node. Before the removal, slow.next points to the node with value 1. After the update, slow.next points to none, effectively removing the only node in the list. Finally, we return dummy.next, which in this case is none, representing an empty list. This concludes the step-by-step execution for all examples. The time complexity of the solution to the problem remove nth node from end of list is O(n), where n represents the number of nodes in the linked list. This is because the algorithm involves three main operations. First, the fast pointer advances by n+1 steps, which takes O(n) time since n corresponds to the list size. Next, both the fast and slow pointers traverse the list together until the fast pointer reaches the end. This step-by-step traversal also takes O(n) time. Finally, the removal of the target node is performed in constant time, O(1), as it only involves reassigning the next pointer. When we combine these operations, the traversal dominates the computation, resulting in an overall time complexity of O(n). The two-pointer approach ensures that the list is traversed only once, maintaining the linear complexity. The space complexity of this solution is O(1), meaning it uses a constant amount of memory regardless of the list size. This efficiency is achieved through careful use of pointers. Specifically, the algorithm uses two pointers, fast and slow, along with a dummy node to manage the traversal and modification of the list. These pointers do not require additional memory that scales with the input size. Furthermore, no auxiliary data structures, such as arrays or stacks, are utilized. The linked list is directly manipulated in place, which eliminates the need for extra space. As a result, the overall space complexity remains constant, making the solution highly space efficient. To better understand the efficiency of the two-pointer approach, let's compare it to a brute force method. The naive approach involves two separate passes through the linked list. First, we count the total number of nodes, which takes O(n) time. Then, we traverse the list again to locate and remove the desired node, which also takes O(n). Although the time complexity of this brute force approach is still O(n), performing two full passes makes it less efficient than the two-pointer method. In contrast, the two-pointer approach achieves the same O(n) time complexity but does so in a single pass by advancing the fast pointer initially. Both methods have a space complexity of O(1), but the reduced traversal in the two-pointer technique makes it the more optimal solution overall. Let's analyze the algorithm in terms of best, average, and worst-case scenarios. In the best case, the input list contains only a single node. Here, the fast pointer quickly reaches the end, and the entire operation completes with a time complexity of O(1), which still falls under O(n), since n equals 1. In the average case, the list has a moderate number of nodes, and the algorithm traverses the entire list once, maintaining a time complexity of O(n). In the worst case, where the list contains a large number of nodes, such as 10 to the power of 4, the algorithm still processes each node only once, resulting in the same O(n) time complexity. Mathematically, the fast pointer's initial movement takes O(n), the traversal with both pointers also takes O(n), and the constant time node removal contributes O(1). Summing these, the total time complexity is O(n). This analysis highlights the optimality of the two-pointer approach, which achieves O(n) time and O(1) space complexity, making it ideal for efficient handling of both small and large input sizes. When solving this problem, there are a few common mistakes to watch out for. First, failing to account for edge cases like an empty list or a single-node list can lead to runtime errors, such as null pointer exceptions or undefined behavior. To avoid this, ensure that your solution explicitly handles these scenarios and test with minimal input sizes. Another common issue is off-by-one errors when determining the target node. For instance, confusing zero-based and one-based indexing can result in removing the wrong node or causing the program to crash. Always double-check your logic for calculating the position of the node to be removed. Lastly, modifying the list during traversal without proper handling is a frequent source of bugs. If you don't maintain references correctly or accidentally skip nodes, you risk breaking the traversal logic. Using techniques like dummy nodes or a two-pointer approach helps prevent these issues and ensures the list is modified safely. In addition to the previous mistakes, exceeding time or space complexity constraints is another pitfall to be mindful of. For example, brute force methods that repeatedly traverse the list can exceed time limits, especially for larger inputs. To avoid this, focus on efficient techniques like the two-pointer method or single-pass algorithms to ensure your solution stays within O(n) time and O(1) space. Another critical issue, particularly in non-garbage collected languages like C++, is forgetting to free memory for the removed node. This can lead to memory leaks, which are especially problematic in long-running applications. To mitigate this, make it a habit to explicitly deallocate memory for the removed node when working in such environments. These considerations are vital for writing robust and efficient code. Many interviewers use this problem to evaluate your understanding of efficient linked list operations. A key pattern they often look for is your ability to apply techniques like the two-pointer method. You might start with a simpler problem, such as finding the middle node of the list, before progressing to removing the nth node from the end. Additionally, it's important to articulate the trade-offs between different approaches. For example, you might compare the clarity of a two-pass solution with the efficiency of a one-pass solution, explaining how you balance simplicity and performance. Always emphasize edge cases during your thought process, such as handling a list with only one node or removing the head node. This shows interviewers that you're thorough in your analysis. Finally, if the problem specifies O(1) space complexity, be explicit about how your solution adheres to this constraint, as this demonstrates your attention to detail. There are several alternative approaches to solving this problem, each with its own trade-offs. The two-pass approach involves calculating the length of the list in the first pass and then traversing it again to locate and remove the target node. While this method is simple to implement, it requires two passes through the list, which may not be ideal for very large datasets. The one-pass two-pointer approach is more efficient, as it uses two pointers. One pointer starts ahead by in nodes, and the other begins at the head. When the leading pointer reaches the end, the trailing pointer will be positioned just before the node to be removed. This method achieves O(n) time and O(1) space but is slightly more complex to implement. Lastly, the recursive approach leverages the call stack to maintain the position from the end of the list. While this method is elegant, it uses O(n) space due to recursion, which may not meet the constraints in all scenarios. It's important to choose the approach that best aligns with the problem's requirements and constraints. Great job completing this problem. To summarize, we focused on efficiently removing the nth node from the end of a linked list, using a two-pass approach. We highlighted key takeaways like the importance of edge case handling and optimizing for both time and space. Keep practicing to master these concepts, and thanks for watching. Be sure to like, subscribe, and stay tuned for more coding content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!